Hi, I am Nazibul, a PhD student at Gagnon Lab in Texas A&M University. Today, I am going to talk about a new low-cost, rapid, and scalable microfluidic fabrication technique, which is called microfluidic pressure in paper, which uses a combination of paper and PDMS sheets to develop new microfluidic devices. I would like to start my talk with a timeline of microfluidic field. Here we see that in 1840, Huygens-Poiseuille equation was developed, which is widely used to characterize fluid flow through microfluidic channels. Then over the years, other relevant technologies such as integrated circuit, the concept of lab on a chip were developed. For today's talk, the two most important events took place in 1998 and 2007, where in 1998, Whiteside's group developed PDMS-based microfluidic fabrication technique, and again in 2007, the same group developed paper-based microfluidics. Over the years, there has been significant R&D engineering in microfluidic field. However, today, if we look at the market penetration, we see that the market penetration of microfluidics is very low, especially in point-of-care diagnostics and also in diagnostics. We think one reason for this low market penetration is a lack of low-cost and scalable fabrication technique. For example, in laboratory, the predominant fabrication technique for microfluidic devices is soft lithography. It takes multiple steps and also it requires a clean room facility. Therefore, it is not scalable and not used in industry. In industry, the predominant technologies are injection molding and hot embossing. However, these technologies require a huge amount of initial investment and there is not much room for product optimization. To mitigate these challenges, paper-based microfluidics have been developed. In paper-based microfluidics, fluid flows through paper channels by capillary action. However, as this fluid flows through paper channels, it starts to evaporate in the external environment. This rate of evaporation depends upon the external temperature and vapor pressure, which varies from place to place. Therefore, the weighting through paper-based microfluidics is not consistent. In addition, the sensitivity of paper-based microfluidics is much lower than traditional microfluidic devices. Therefore, we thought, can we combine both paper and PDMS and come up with a fabrication technique that is low cost and scalable, and the device performance of the devices fabricated using these techniques will be reliable. To do that, we came up with a technique that combines both paper and PDMS. We take a piece of paper and we use laser cutter to cut precise paper channels. Then we sandwich those paper channels in between two PDMS sheets. Next, we use a combination of Tesla coil and heat press to encompress that paper channel in between these PDMS sheets. And we end up with a novel type of microfluidic device, which we call, and this fabrication technique we call microfluidic pressure in paper or micropip. Here is the example of a gradient generator that has been developed using our micropip technology. And we see that the fluid flow performance is similar to that of traditional microfluidic devices. Next, I want to give a brief overview of the theoretical background for pressurized fluid flow through paper channels. For traditional paper-based devices, Lucas-Wasburn equation is widely used. Lucas-Wasburn equation takes into account the fluid flow due to capillary action. However, it doesn't take into account evaporation rate. Therefore, in 2015, Liu et al. Developed a new model that takes into account both fluid flow through capillary action and evaporation of fluid in the external environment. For our device, we have used a combination of Lucas-Wasburn equation and Darcy's equation. As I have mentioned earlier, Lucas-Wasburn equation takes into account fluid flow due to capillary action, and Darcy's equation takes into account pressurized fluid flow through a porous medium. Next, we developed a low-cost pressure system that uses in-house air for fluid flow through microfluidic devices. This whole system cost around $500 to build. Next, we wanted to characterize fluid flow through paper and see if our experimental data matches with our theoretical model. To do that, we had a straight paper channel and we flowed blue dye through our paper channel. And we took images of the fluid front at different time frames. Next, we plotted our experimental data with our model. At first, we plotted the experimental data with the existing evaporation model, and we see that our experimental data matches with the evaporation model. That means our experimental setup is ready for other experiments. Next, we wanted to see what happens if we incompress the paper channel within 2 PDMS sheets. So we incompress the paper channel within the PDMS sheets and let capillary action to see how the fluid flow through the paper. And we see that the flow rate is much lower than an open paper channel. This is because as the paper is incompressed between 2 PDMS sheets, the effective pore size of the paper decreases. Here, the effective pore size takes into account the block pores and the variation of porosity and cross-sectional area due to wetting. Next, we wanted to see how this fluid flow behaves if we have an external inlet pressure. So to do that, we used 2 different inlet pressures, one at 0.5 psi, the other one at 1 psi, and we see that our experimental data is in good accordance with our theoretical model that I have shown you previously. Next, I wanted to show few examples of the devices that were fabricated using our micropip technology. So one of the major limitations of traditional paper-based devices is that it cannot be reused. Since fluid flow through traditional paper-based devices takes place due to capillary action, so once these devices are fully wetted, they cannot be reused. However, in our devices, we use an external pressure system. So to quantify the reusability of our paper-based devices, we used a PBS solution of a known conductivity. We flowed the PBS solution through our devices and we measured the outlet conductivity. Then we used DI to rinse the whole device. We dried the device and we reused it for a different PBS solution of a different conductivity. So for the first run, we used a PBS solution of 1100 microsiemens per centimeter conductivity, and we measured the outlet conductivity. Then we rinsed it with DI, dried it, and we used a PBS solution of around 500 microsiemens per centimeter conductivity. We again washed it with DI, and finally we used a 50 microsiemens per centimeter PBS solution. And we see that the outlet conductivity is in good accordance with the inlet conductivity. Then we used a bright field microscope to take the image of the paper structure before and after 3 times use to see if there is any structural damages inside the paper pores. And we see that there are no structural damages of the paper device. Next, we wanted to see, can we do the same operation in a continuous manner for a long time? So for this particular experiment, we ran the whole experiment for more than 70 minutes, and we can see that the paper device we can run the paper device for 70 minutes, more than 70 minutes, excuse me. So we started with 100 microsiemens per centimeter inlet conductivity, and we measured the outlet conductivity. After some time, we step changed to 500 microsiemens per centimeter inlet conductivity, and we see that as we change the inlet conductivity, the outlet conductivity also decreases. And finally, we use DI, and we see as we introduce DI, the outlet conductivity also decreases. So we think that our paper-based devices can be used for a long time and with buffer solution with different conductivities. Next, we wanted to see if these devices are biocompatible or not. So to do that, we used bovine red blood cells suspended in PBS solutions, and we flowed the red blood cells through our paper devices. And then to see if they can be reused, what we did is that we used DI to clean the paper devices. Then we stored the paper devices overnight, and the next day we again flowed bovine red blood cells suspended in PVS solutions. And then we measured the flow characteristics of the paper devices. We see that from use 1 to use 2, the flow rate of the paper devices slightly increases. We think this increase in flow rate is due to a slight increase in porosity due to fiber swelling, which takes place when the fibers get wet. Next, we wanted to integrate electrokinetic operation into our micropip devices. So to do that, we used low-cost copper tapes as electrodes, and we developed a simple device with 1 inlet and 2 outlet. So here the black arrows are the electric field lines. So here we have 1 inlet and 2 outlet. We used a positive electrode in one of the outlets, and we used the copper tape as the negative electrode. And we used Alexa red dye, which is negatively charged, and we flowed it through our paper device. And we see that as we introduce an electric field, the dyes inside the inlet channel starts to deflect, and they start to move towards one of the outlets. We used a DC voltage generator, and we used different voltages to see how this movement of dye takes place. Here we see that as we increase the voltage, the deflection also increases, and at 300 volt, all the dyes flow to one of the outlets, and none of the dyes flows towards the other outlet. Here is a video of charge dye deflection inside a paper device. Next, we wanted to see, can this simple setup can be used for charged biomolecules. So to do that, we used a DNA solution. Since DNA is negatively charged, so DNA can be concentrated in one of the outlets. So we used a 100 volt DC voltage, and we ran the DNA solution through the paper channel for 20 minutes. And after 20 minutes, we collected the paper from one of the outlets, and then we used qPCR analysis to see how much increase in DNA concentration takes place in one of the outlets. Here is a fluorescent image where we can clearly see that there is a deflection of DNA concentration, and the DNAs are concentrated in one of the outlets. So here are the qPCR results, and we see that using only 100 volt and only in 20 minutes, we can see a 30-fold increase in DNA concentration in one of the outlets. Therefore, we think that we can use this simple operation to concentrate DNA, and we can enhance qPCR performance. Next, we wanted to see, can these paper devices be used in oil and gas industry? We have developed this simple paper device, which we call reservoir on paper, where at first we saturate the paper devices using crude oil that was generously donated to us from Petroleum Engineering Department. Next, we used a brine solution coupled with blue dye and flowed the brine solution through the paper device. And we see that as brine flows through the paper pores, it displaces the crude oil present there, and the crude oil comes with the blue dye through the outlet. And with time, this rate of displacement increases. We were able to develop a calibration curve, and we were able to develop a percentage recovery of crude oil over time. We believe that this simple device can be used by oil and gas industry on site, where the industry people can use different brine solutions or other flooding solutions comprised of different polymers inside that flooding solutions, and they can use different flooding solution to figure out which flooding solution works best for that particular oil field, and use these simple devices to optimize their operation. So in future work, we want to develop a benchtop device that will have all the pressurized system and analysis system. And we want to have these credit card size micropip devices that will have all the operations inside of them. So we will put these credit card size devices into our benchtop device, and it will do all the analysis and give us result. That's all for my today's talk. At the end, I would like to thank my PI and my group members for their continuous support and encouragement.